Ramadan, Ridwan, and Taufik Ashidiki from Bandung Polytechnic for Manufacturing, Indonesia. So please, Mr. Nur Jamiluddin.
Yeah.
Please, the stage is yours. The time is okay.
Bismillahirrahmanirrahim. Good afternoon, ladies and gentlemen. It is an honor for me to be able to attend today as a presenter at the International Conference on Mechatronic, Robotics, and System Engineering 2021. First of all, I would like to say thank you to morse 2021 committee for giving an opportunity to present our work in this conference. Okay, let me share screen. This research is motivated by the needs of industries in the current industrial 4.0 era by implementing autonomous biorobot, and the algorithm SLAM or simultaneous localization and mapping is very popular method to control mobile robot, and we focus on the wire-based SLAM, which is a visual-based SLAM. This research purpose is learn how wire-based SLAM 2 algorithm as a visual-based SLAM generate environment map from image data, and then to implement wire-based SLAM 2 algorithm in Robotino mobile robot with monocular camera sensor and evaluate the map result from the system and compare it with the real state of the robot environment. This is the system overview. It's simple. We use Logitech webcam series C920 monocular camera mounted and attached to the Robotino 3 mobile robot with ROS or robotic operating system installed. And then the Robotino will communicate wirelessly to the server computer. This is the hardware used. We use the Robotino. Robotino is the mobile robot platform for research and education manufactured by Festo Didactic. With its omnidirectional drive sensor, interface, and application-specific extension, Robotino can be used very flexibly. The most important programming language and system are available for programming individual application. Robotino has a bumper sensor around circumference, infrared distance sensor, a color camera with figure resolution, and many more sensors. So for signal input and output, Robotino has several interfaces like USB, Ethernet, EIC digital and EIC analog inputs, EIC digital output, additional motor output for driving high loads, additional encoder, and the power is supplied by two 12-volt 5 ampere battery. And in this study, we use Ubuntu 18.04 as the operating system and the ROS melodic. ROS is the open source robotic programming framework work in Ubuntu operating system, which is used for input and output control as well as robotic communication. The ROS system starts by initiating the computer as master. Then the computer also executes the keyboard teleop node for the robot. And then the Robotino node, wire-based SLAM mono, and Robotino camera node are executed on the robot. The keyboard teleop node will send a topic or the data named CMD file. This is the command velocity to the robot via the Robotino node. The topic carries a message, command, the movement to the robot, both linear and angular movement, so that the robot can move with its camera to explore the environment. The camera is commanded by Robotino camera node, so that it can send the data with topic image raw to the topic ORB/2 mono. It is not the image is computed so that it becomes the data need to create a map. Like a map, point, robot position, and orientation. Image processed by algorithm and the robot trajectory. This is the picture. It's the flow diagram of the ROS system to create the map using the ORB/2 algorithm. This is the system flowchart of ORB/2. There are three main program or three main algorithm, which is tracking, local mapping, and loop closing. And then in the end, it will be bundled by the full bundled adjustment to update the map. As you can see, the system take the frame, the image raw from the camera, and then they process it by the tracking algorithm, and then it will get the keyframes. Keyframe is the data represent the point in the world environment. And then it will be executed by the local mapping algorithm and then the loop closing to create the map representation of the environment. In order to project the coordinate of the 3D world onto the drawing plane, we use pinhole camera model. The image is placed at distance f from O, where f is the focal length of the camera. Then it considers the point P, XP, YP, and ZP in this coordinate system. If we consider a two-dimension coordinate system in the drawing plane with the center at point R, which is the intersection of the axis of the 3D world coordinate system and the point Q, you get XQ and YQ in the drawing plane. This image shows the pinhole camera model. The R and T metric have a very important role in both visual odometry and SLAM visual system. This is the algorithm of FAST. Basically, the ORB is acronym of oriented, fast, and rotated brief. So we have two main algorithms. The first is oriented fast. Fast, or the acronym of features from accelerated and segment test algorithm run as follows. Given a pixel P in an array, and then the fast compare the brightness of P to surround 16 pixels that are in a small circle around P. Pixel in the circle is then sorted into three classes. And then the key point found by the fast give us information of the location of the determining edge in an image. And then the fast feature do not have an orientation component and multi-scale feature. So ORB, or oriented rotated brief algorithm, use a multi-scale image pyramid. Once ORB has created a pyramid, it uses the fast algorithm to detect key point in the image. By detecting the key point at each level, ORB is effectively locating key point at a different scale. After locating key point, ORB now assign an orientation on each key point, and then brief, or acronym of binary robust independent elementary feature, take all the key point found by the fast algorithm and convert it into a binary feature vector, so that together they can represent an object. The ORB/2 algorithm is implemented in the Robotinum by robot to generate map of the environment. The system is aimed to be able to detect object by projecting this object onto a map created by the system. It is the result its implementation, the system succeeds in building the map point to resemble the shape of the object profile. The figure show a set of map points that form an environment object, which is a gallon of water, and then this profile has a circular base with the coordinate at the center of point 0.437 and 0.122 and minus 0.078 with a height on the z-axis 0.002 with range of minus 0.078 to 0.095. And then we also implement or try another object. This is the figure of block shape profile. And then the system successfully create the map points represent the object in the environment.
Sorry, Mr. Jamiluddin, your time is
Okay, I will.
5 minutes more.
Then we also do the measurement. Previously, this measurement is carried out by intention of knowing the comparison between the actual object and then the dimension of the map. The results scale the real object dimension. The tables show the result data in the comparison between object dimension in map. We get the ratio of the real object and the represent object in the map is 1 per 5.81. So the conclusion is this experimental research proved that WireBitSlim2 algorithm can be implemented to an AMR or autonomous mobile robot to perform SLAM, or we know SLAM is simultaneously localization and mapping, which is using a monocular camera as a sensor. The system is able to represent object in its environment into a map with ratio between map dimension and actual dimension of 1 per 5.81. Where WireBitSlim2 algorithm implementation was managed to create a map and do localization. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you, Mr. Nur Jamiluddin. Perhaps because the time is very strict.
Yeah.
We must follow to second presenter, I think. Yeah. We can discuss this time. Okay, Mr. For second presenter is Machine Mapping Based Modified Depth First Search Algorithm Simulator for Agricultural Environment, and I think will be presented by Mr. Justin Sunarto Budiman, I think.
Yeah.
Yes. Okay. Mr. Justin, the time is yours.
Okay, thank you.
15 minutes maximum, yeah.
Yeah.
Okay, thank you.
Okay, hello ladies and gentlemen. My name is Justin Sunarto Budiman from Parahyangan Catholic University Indonesia. Now I'm going to presenting about our research, mesh mapping based modified depth first search algorithm simulator for agricultural environment. Introduction. The first is autonomous mobile robot has been widely used in various fields. The various field can be seen in figure 2. And recently, the autonomous mobile robot has been used for smart farming to carry out agricultural tasks such as seeding and harvesting and crop monitoring and inspection. And to be able to carry out its duties, the MR must have the ability to map the environment. The MR research on mapping is related around the mesh solving, robotics using the variety of algorithms, which is classified into 2 groups. The first group is the known mesh environment algorithms, and the second group is the unknown mesh environment algorithms. In order to test the proposed mesh solver algorithms, a mesh is physically built and the mobile robot is programmed using the proposed approach. But by physically build the maze and the robot, we might there might be some risks. The first risk is to build a rat maze, we need a large room availability and a large cost. And also the second risk is the maze and the robot will be damaged, might be damaged when testing process due to mechanical and software error. Therefore, in order to test the algorithm without risk, in this research, we developed a Python-based simulator for simulation of sensor-based mobile robot for mapping an agricultural landscape. This landscape is considered from robot's point of view and considered as an unknown maze. So the plants will be representing by the wall. The description of our systems is the first, the robot has 4 heading direction, north, east, south, and west, and there is a set of priority moving rules while the robots move in the maze. In figure 4, the moving priority, the first one is move forward 1 cell, the second one is turn right, then move forward 1 cell, the third one is turn left, then move forward 1 cell, and the last is turn around, then move forward 1 cell. In figure 5, we give you an illustration about the robot movement with priority. There are 3 conditions with labels 1 until 3. The first condition is when the robot facing east, there are 2 available ways on the front and the right side of the robot. Therefore, the robot will follow the first priority to move forward. The second condition is the robot is facing east and the robot is located at the dead end cells. That means there is no other possible way and the robot will follow its 4th priorities to turn around 180 degrees and moving forward 1 cell. And the third condition is when the robot facing north, there are 2 available ways on the left and the right side of the robot. And by following its second priority, the robot will turn right and move forward. For simulator purpose, the input of our systems are robot's heading, left, front, and right sensor signals, and XY coordinates of the robot's position. Also, we use 3 lists called visited list, depth list, and depth core for record keeping. The visited list stores the already visited cell coordinates, and the depth list stores cell coordinates that have more than 1 possible way, and the depth core stores unvisited cell coordinates. The flow diagram of the simulation, the first process is wall scanning to find all the possible way that the robot can take, and the second is print the scanned wall. In simulator, the wall represented by white blocks. The third process is check current coordinate on visited list. If this current coordinate is not present in visited list, the robot will record these coordinates and execute smooth subroutine. But if this current coordinate is present in visited list, the robot will check depth list. When the robot check depth list, if there are any coordinates recorded in depth list, the robot will execute depth case subroutine to move to the last coordinate recorded on depth list. But if there are no other coordinates recorded on depth list, the robot will execute go home subroutine. Next is the moving decision. The move subroutine decides the moving decision of the robot based off heading and sensor information. Table 1 represent all the possible combination of the sensor, which 0 represent the possible ways and 1 represent a wall. So in figure 6, we give you an example about how the sensor read the condition of the environment. In figure 6a, the decision is to move forward 1 cell and write the robot current coordinates to visited list because there is no other ways on the right or on the left of the robot. And from figure 6b, the decision is to move forward and write the robot current coordinate to visited list and write robot's right coordinate to depth list. Note that each coordinate in visited list and depth list has unique sequence number. And we use this sequence number in depth case subroutine. When the robots arrive at a junction, its unvisited list is recorded in the depth list. And we use three variables namely CF, CR, and CL, and used to represent the left, front, and right situation respectively. In figure 7, we give you an example about how CF, CR, and CL use. If there are no other way, no possible way on the right or on the left side of the robot, like figure 7a, the value of CL and CR will be nil, and the CF will be equals to val. Val in here equals to sequence number of unvisited cell, minus sequence number of the possible way in current robot position. By using a subtraction method, we determine the movement of the robot. The robot will move to the cell with the smallest value in the depth away list. The next is when the robot has visit all the cell in the maze, the robot will execute go home subroutine, which also use CF, CL, and CR variable, and the file value of this subroutine is 0, which represent the sequence number of initial location of the robot minus sequence number of the possible way in current robot position. In the subroutine, the robot will move to the cell with the biggest value in the go back list. For the simulation and analysis, we use the figure 9 maze as our maze and in this research. And before we start our simulation, we need to determine the robot heading and then the robot location. In figure 10, the robot heading is east and the robot location is minus 264, 264. The robot will continue moving on the maze by following its priority and also environment condition until the robot is located at coordinate minus 24, 224 in figure 11. In this condition, the robot found a junction at coordinate minus 72, 264, which is represented by point A, and the robot will record the right coordinate of the robot to the depth list and continue to move along the maze until it found a dead end cell. In figure 12, the robot have found a dead end cell and moved along by following its fourth priority to turn around 180 degrees and move back to coordinate that in depth list. Since the only coordinate on that list is point A, the robot will moving back to point A. And
excuse me, 4 minutes more.
Okay, and then the robot will continue to moving by turn left, and eventually the robot will arrive at point 72, 120 in figure 13. The only cell in figure 13 is point C. Then the robot must turn right and go to the point C as the last cell in the maze. After the robot arrives at point C, the robot will execute go home subroutine with the shortest path available in the maze. And in figure 14, the robot found the shortest path on the maze is C, B, A, and then initial position. Conclusion and future works. The simulator can visualize the robot maze mapping operation by showing the mapping results in the simulation area. And by using the DFS algorithm, all the cells in the maze can be mapped. However, the proposed simulator still has some limitation that will become our future works to overcome such limitation. And for hardware, we also considered a sensor that will be used. Typically, an ultrasonic sensor can sense a wall or obstacle. But since the vegetation is in an agricultural landscape may vary, we will investigate the appropriate sensor that accurately detects a wall or veggies in the agricultural environment as future works. We will also study the possibilities of using camera and image processing so that the turtle movement decision in the simulator area will be sent to the robot so that the robot movement will be the same as the turtle in simulator. That's all for me. Thank you.
Okay, thank you. For attendee, any question for these papers? I think it's very interesting. But I will give you to yeah to if anyone have any question to Mr. Justin. Okay. Is there no question? I will I will continue to next presenter, Mr. Gede Haris Widyarta, I think.
Thank you so much, Mr. Ali.
Okay. The article. Thank you for Mr. Justin. Yeah. And we will continue to the third participant. The title is Control Lyapunov Barrier Function Implementation for Mobile Robot Model with Hardware in the Loop. So, Mr. Gede, the time is yours.
Okay.
Thank you.
Can I share screen?
Yes.
Okay.
Okay.
Okay. Can you see my screen?
Yeah.
Okay.
Okay.
Okay. Good afternoon, ladies and gentlemen. My name is Gede Haris Widyarta. I am a fresh graduate student from Telkom University, and today I will explain you about the research titled Control Lyapunov Barrier Function Implementation for Mobile Robot Model with Hardware in the Loop simulation. So, in this research, it consists of 4 authors. There are Gede Haris Widyarta, myself, and Mr. Muhammad Zaki Ramloni, and then Muhammad Ridho Rosa, and Mr. Bambang Rianto Trilaksono. So in this research, here's the table of content. First, we go to the introduction, and then literature review, then system design.
Sorry,
then,
Mr. Gede.
okay.
I think the right part is blocked by some object, I think.
Okay, wait.
The right part of your presentation is blocked.
It's
Maybe some windows.
Is that clear?
Okay, it's okay.
Okay. I will continue. The last one is the conclusion. Okay, we go to the first one, introduction. So, mobile robots are one of the most widely used types of robot in industry. The main feature of the mobile robot, besides navigation, is the collision avoidance feature. So, to design a collision avoidance system, an appropriate control system is needed for the mobile robot. Based on these problems, a simulation of mobile robot model with a control method is essential to see the response of the mobile robot system. In this study, control method to be applied to the mobile robot is control Lyapunov barrier function, or we call CLBF. We use CLBF because CLBF has an advantage that it can reach the point of the stability in all initial stage and maintain system safety by avoiding barrier and reaching the destination point of the mobile robot. The primary reference for this research is the CLBF study in 2014 by Mr. Zaki and Mr. Bayu Jayawardana. So the researcher combined the method of the control Lyapunov function and control barrier function, which were then combined into control Lyapunov function. And then the result obtained are that applying the CLBF method in a closed loop system, it can reach a point of stability and ensure system safety by avoiding unsafe state through simulation. Here's the literature review. So in this research, we use one assumption for the mobile robot. In this study, the mobile robot model is assumed to be a system single integrator, where the mobile robot dynamics equation, or we call FX, is not used in the control system design. So the mobile robot dynamics equation will behave at 0 value, and GX, or the matrix input, is a second order identity matrix. The purpose of giving the assumption of single integrator system on the mobile robot model is to simplify the mobile robot model and produce an output in the form of position, which is the input for the CLBF. Then a closed loop system is formed as the figure I show you on the slide. So the mobile robot system with a single integrator system assumption has an input can be stated as U1, sorry, is the velocity of state x1 or the velocity of the horizontal axis x. Meanwhile, U2 is the velocity of the state x2 or the velocity on the vertical axis y. So control Lyapunov Barry function. As I mentioned above, the CLBF method is one of the modern control methods initiated and developed in 2014, and the CLBF method combines two control methods, namely control Lyapunov function and control Barry function. The purpose of CLBF method is to obtain system stability and ensure system safety. CLF is symbolized by Px, CBF is symbolized by Bx, and CLBF represented by Wx. So CLBF equation can be represented as the equation I show you on the slide. Wx equal Vx plus lambda multiplied by Bx plus kappa. On the equation, Vx is the CLF equation, Bx is the CBF equation, lambda is the gain barrier parameter, where the higher value of the lambda is given, the more aggressive the system when avoiding the barrier. And the kappa is an additional control parameter. If the state is positive and kappa more than 0, then the system distance to the barrier will be closer, while when the kappa is less than 0, the system distance to the barrier is greater. In this study, CLBF also has an input in the form of mobile robot coordinate position in x and y axis and can be expressed as x1 is the mobile robot position in x-axis and x2 is the mobile robot position in y-axis. Okay, here's the hardware in the loop design. So hardware in the loop is a simulation method that uses hardware and software with the aim that your simulation result will produce values that are close to the actual test result in the actual environment. In this research, the design field simulation used the actual controller on the Arduino and a virtual fan on the Simulink. For data communication, we use the AKI or data acquisition device. So the step hardware in the loop, I divided into 4 steps. The first one is Arduino as an actual controller. We will send a control signal in the form of PWM or pulse width modulation. And then the control signal from the Arduino is converted into an analog signal with a DAC circuit or digital analog converter circuit. Then it's distributed to the AKI. And then the AKI controls the virtual plant on Simulink to run according to the control signal given by Arduino. And the last one, Simulink will provide a feedback signal to Arduino via the AKI. Then Arduino can process a new control signal. Okay, the next part is the system design. So we begin with the CLF equation. The CLF equation in this study can be expressed as Vx equal x1 square plus q multiplied by x1 and x2 plus x2 square. So this model is taken from the research in 2014, but we modified it by multiply the equation with q coefficient. So the q coefficient has a value of 0.001 until 0.1. The coefficient values is obtained from the result of trial and error experiments. So the closer the q coefficient to 0.1, the smoother the result. Then the CLF model is checked whether it has definite positive or negative, because to form a CLF equation, the value has to be definite positive. So from the CLF equation above, we take the 0.1 value for the q coefficient, then the derivative are obtained as LFV equals 0 because the dynamics for Fx is behave at 0, and then LGV is partially derivative from the CLF function to Gx, and Gx has a value for the identity matrix second order, so it has a value as you can see on the slide. And then we go to the CBF equation. The CBF equation in this study use the circular barrier equation because the barrier is in circle shape, so we use the circular barrier equation as represented by Dx, and M and N is the center of the point in the circle in the x and y coordinate. So the Lie derivative value for CBF is obtained as I mentioned in the slide. So LFB is once again is 0 because fx is 0, and then LGB has a value because Gx is the second order identity matrix, and the value depends on M and N itself. So then after the CLF and CBF equation are solved, these equations are substituted into the CLBF equation. Then CLBF Lie derivative can be expressed as LFW is 0 and LGW is LGV plus lambda multiplied by LGD plus kappa. So here's the Hill experiment setup. I divided into 4 parts or 4 devices that I use. So the first one is PC. PC used to design and run the virtual plant through Simulink application. The second one is the AKI to start a communication between the virtual plant and the actual controller. And the third is the digital to analog converter, or we call the AC, to convert digital signal from the Arduino in the form of PWM to analog signal. And the last one is the Arduino Mega used as the actual controller for the virtual plant in the Simulink. Okay, here's the virtual plant. I explain it and describe into 4 parts. So the first block or the first part is the control signal receiving block from Arduino. And then the second block is a scope block that serves as a position and control signal data collector, then visualized into chart. And then the third is the single integrator system block, where the mobile robot is assumed to be a single integrator system. And the last block, block number 4, is the block for sending the output from the virtual plant to Arduino. Here's the system flow chart. On the left side is the virtual plant on Simulink flow chart, and the right side is the Arduino as the actual control flow chart. So we begin for the left side first. The first step to run the Hill simulation is to enter initial condition value. Then the virtual plant in Simulink is run. Simulink will receive a control signal from Arduino with the help of the AKI device, and then the virtual plant will process and produce output according to the received control signal. In addition, the virtual plant also sends output data to Arduino via the AKI device. If the simulation time runs for 4 seconds, the Hill system will give a stop scope command to visualize the output state and the distance data between the system and the barrier. So on the right side is the flowchart color. The initial stage initializing the system for declaring control parameter values, and then Arduino receive the output state from the Simulink with the AKI. From the value received, the process of the CLBF method continues and produces control signal outputs, which are then sent to Simulink via Arduino PWM pin and the AKI device. Here's the result and discussion. Okay, on the table, you can see the control system specification that we use. First, we have the CLF equation with coefficient Q is 0.1, and then CBF equations. There are 2 CBF equations because we use 2 circular barriers, and then CLBF equation as I mentioned above. And then we got 3 control parameter. There are lambda valued by 2, kappa is -1, and gamma is 1. Gamma is the parameter to multiply the output. So 5 initial conditions were taken for simulation with MATLAB and the Hill system to test the virtual plant on Simulink. And to determining the control parameters value for the lambda, kappa, and gamma, the author used the trial and error method by looking at the effect parameter values on the Hill simulation result. Okay, here's the result. The right one is the simulation result, and the left one is the simulation result, and the right one is the hardware in the loop. As you can see, there are 2 barriers in circular shape. This one is this one, and 2 figures shows the result of the pathway plot taken by the mobile robot system model during the simulation and Hill with 5 different initial conditions. The 2 images both show the mobile robot system with the single integrator system assumption successfully avoids 2 existing barriers and goes to the origin or the destination point at 0.0. And from 5 initial conditions, we can take one of them. For example, we take the third initial condition to see the control output and distance graph. Okay, here's the output. The right side is the distance to various graphs, and then the left side is the child wave output. So the child wave output, I will explain first. The left side is the graph for the output control signal U1 and U2 from the Hill simulation. It can be seen that the time on 0.1 until 0.5 seconds, the system has significant value, increased value of this control signal because the system is approaching the barrier. Then when the time is on 1.5 seconds, the value of the system controls approach the stability point at 0. Also, in the figure on the left, the control signal generated by Hill has a noise caused by data transmission communication from Arduino to Simulink and vice versa. And then on the right side, there is a distance to barriers graph. So from the figure, we know the system avoids the barriers from the two graphs because the distance often is not negative or less than 0. In the first barrier that shows on the blue line, the closest distance of the system is 0.069 meter. And in the second barrier, the closest distance is 0.49 meter. Thus, the system does not hit the barrier and can avoid it. So I conclude the system safety is maintained. Okay, here's the data result summary. As you can see, the simulation result is better than Hill result. This is because in Hill we use actual controller, so there are many factors that influence the output system. Okay, conclusion. So the conclusion, the mobile robot dynamics is assumed as a single interrogator system. The proposed method shows the mobile robot can reach the origin and avoid the obstacle that verify the stability, proof, and its safety. The average percentage level of error resulting from the system testing with Hill is 3.89%, and closest distance to the barrier is 1.05 meter for the first barrier and 0.5 meter for the second barrier. And the future work, I hope Hill simulation will, with mobile robot, can use a complete mobile robot model, including dynamics and kinematics equation, as well as having dynamic barrier and the real implementation of a mobile robot assuming a single system integrator with child wave control can be realized in hardware form and tested in real environment. Okay, maybe that's all for me. Thank you.
Okay, thank you, Mr. Gede. Any question from all attendees? Any question? Okay, I think I'm interested in your research. Why the result from simulation and from Hill is very different? The error average is 2%, I think.
Yeah.
Error average is different 2%.
Okay. Thank you for the question. I will try to answer my best. So the difference between the result difference between simulation and Hill, I think it caused by so many factors such as data transmission, delay, and then because it transfer data in wireless way, so I think it's because the delay in data transmission.
Oh, okay, I see. The delay in data transmission, yeah.
Yeah.
Okay. And so maybe for processing time in Arduino.
Pardon me, sir?
Processing time in Arduino. Is there any factor?
Oh, yeah. Yeah, I think the processing time in Arduino is also influence the result because the code that I read is so long, and I think there is also influence the result of the system.
Okay. Yes, perhaps one day you can shorten your program, right?
Thank you, sir. Thank you for your advice.
Okay, thank you for the presentation. And now we continue with the fourth paper. Title is Path Following Control of an Autonomous Bus Based on Lyapunov Stability Function by Nadana Aisyah Aziz from Bandung Institute of Technology. Okay, the time is yours, Nadana.
Okay, thank you, Mr. Ali, for your time and place. Let me share my screen.
Yes, of course.
Okay, can you see my screen, Mr.
Yes,
Ali?
yes, yes.
Okay,
Okay,
thank you. Thank you.
please.
Wait. Okay. Bismillahirrahmanirrahim. Hello, everyone. Okay, in this beautiful day, I would like to go for my, our presentation with title Path Flowing Control of an Autonomous Bus based on Lyapunov Stability Function. This is a research by me, Nadana Aisyah Aziz, and my fellow Joshua Friendly, Fahmi Rizaldi, under the supervision of Mr. Augie Widyatmo and Mr. Yulunasi Nazarudin. We are from Instrumentation and Control Research Group, Institute Technology Bandung. So this research will introduce a method regarding the movement control of an autonomous bus through a path flowing algorithm, which is designed based on the error stabilization of position and orientation of the bus using Lyapunov stability method. Okay. This research is supported by Kemendikbud Ristek of Republic of Indonesia under Fundamental or Applied Research Team 2021 and in part by the research program of Institute Technology Bandung. And the outline of the presentation is shown as follows: that are introduction, and then deriving the path flowing control algorithm, then simulation and implementation results, and the last is conclusion. So we first move to the introduction. So over the past few years, public transportation has been a serious matter to be solved in Indonesia. For instance, in Jakarta as the capital city of Indonesia. From the data from Indonesia Central Bureau of Statistics, the number of motorized vehicles in Jakarta has reached 80.6 million units. From the demographic you can see in your screen, from all the registered motorized vehicles in Jakarta, only 2% is bus. Only 2% of it is bus or public transportation. So the result of the insufficient number of public transportation is severe congestion. So we get data that in average, people can spend about 55 hours move on the road per year only on the road. And then we can propose the solution is mass rapid transportation, which can mobilize a large number of people and reduce the space taken by the vehicle. And as we move to the autonomous system era, so we can direct to the autonomous bus to be the solution of this problem. As autonomous bus over efficiency, reduce environmental impact, cost saving, reducing congestion, and increase the reliability of the bus. And also, the autonomous bus will be used in the future in the capital city in Indonesia. So I think this research is important and aligned with governance program. So in this paper, we propose an alternative control method for forward-moving maneuver of autonomous bus, where the control objective is to align the head of the bus to the desired path. We will model and measure the kinematic error of the position and the orientation of the system. And also, the objective of the control is to achieve the origin of the error. And we use Lyapunov stability theorem. By using this, the origin can be characterized if it's stable, if it's asymptotically stable or unstable. So we also introduce an objective function to optimize the control parameter. Okay, now we move to the path following control. First, we introduce the kinematic model of the forward-moving maneuver bus. So as you can see in the right side of the screen, this is the model of the bus. The system is a rigid body with length L, which is the difference distance between the front wheel and rear wheel. And this is also the reference point, the center point of the front wheel, expressed by variable h, and the theta here is the orientation of the system, which is the angle of the x-axis to the position vector t. Basically, the bus is controlled by two inputs which are the traction velocity v and steering angle alpha x. And we made two assumptions here that the rear wheel drive system is assumed to be differential wheel, and the second, the steering angle input is constrained between minus p by 6 and plus p by 6 due to its steering movement capability. And this is the kinematic model of the. Okay, after we deriving the kinematic model of the bus, here we derive the path following objective. So in deriving the controller function, we use Lyapunov stability testing to perform to observe, whether the system is stable or not after implementing the controller function. So if you see in the right side of your screen, this is the bus, the model of the bus, and this is the path P with a certain position and orientation. And we introduce also the error of position, which is the deviation of the reference point of the bus and the path, and the error of the orientation, which is the deviation between the orientation of the bus and deviation of the tangent of the P-line curve. Okay, after this we can, basically the definition of the stability and objective of this controller is to make the origin of the system asymptotically stable, or the error is zero. So we can derive the kinematic equation defined as follow, and by the Lyapunov stability theorem, we can derive the first derivation of Lyapunov like this, as shown in equation 3. So if you see from the equation 3, you can see that the system is basically unstable at the equilibrium point, or in other words, the system will not be able to go to this condition in accordance to desired path. So to handle this, we also introduce steering control function that can make the error of the position and error of the orientation zero, or in other words, the first derivative of the Lyapunov function is greater than zero. So the variable steering angle alpha is defined as this, and if we substitute this steering angle to the derivative of Lyapunov in the previous slide, we can get this p dot as minus k times error of orientation square. You can see this, it contains k, with k can be any positive number, I think, okay, this means that the value of p dot is less than zero, or semi-definite. So, based on the Lyapunov stability theorem, the point of error of orientation can be asymptotically stable, because of when time is infinite, the value of error of orientation also goes to zero. And then we can see this is the steering angle contains k. So here we conduct optimization of k to find out, to obtain the optimal k, which with this objective function, the objective function is to minimize the error of position and error of orientation. So we can see the most optimal system performance. And to get to get proof or error position to be zero as well, we can substitute the ring angle to the kinematic error so that we can see this. And as error of orientation is zero, so error of uh, derivative uh, derivative error of the position is also zero, and the position error value will go constant value, and error of the orientation is zero. Okay. Next, we also derive the traction velocity control function. This controlling traction velocity is needed to make the movement of the system not too aggressive, especially where the error of the system is too large. So this is the traction velocity control function. So after deriving all the algorithm, we will conduct the simulation and real-time implementation. The simulation and real-time implementation will be conducted in two types of paths. Okay, this is the first part. This is the first part. This is the straight line, and the second part is three segment lines that form an S shape as shown in this figure. The first part is function with desired position y 135 cm, and the orientation is 0 degree. And the position and orientation of the second part you can see in here. That the first segment is x x is 240 centimeter with orientation of 90 degree, while the third segment has desired of y is 380 centimeter and orientation with theta 0 degree. Okay, so the real-time experimental investigation was also conducted in this research to verify the path control algorithm. We use miniature scale bus made from EV3 bricks. This is the picture of the miniature with some sensors around it. This resembles the real bus with length and width the miniature is 39 cm and 55.5 centimeter. So this is the experimental setup. All the sensor here, not MCU is on the top of the miniature bus, is sent to the computer using MQTT protocol. And in the computer, we use MATLAB to build the algorithm, and we send back the input control or input law to the bus, to miniature bus to see MQTT as well. And then we move next to the right side here. This is the block diagram of the system. So basically, this is the desired position and design orientation, that point I mean, and this is the output. The position and the orientation of the bus is sent using indoor position system, and then it fed back to the path following controller. And here we also compare the output of the system with the set point. So it exhibits error or it produces error, and we use error we use the error to produce the input law. Okay, after path following controller to the algorithm, then the input law is produced and it fed back to the actuator of the path. And then the simulation and implementation also conducted with three themes. First is the first path simulation and real-time implementation with various of k value. Then the first path simulation and real implementation with various initial conditions. And the third is second path simulation and implementation with various value of k also. So we move next. This is the simulation and real implementation result. This is the first path simulation with variation of k. We use a variation of k that are 10, 20, 40, and 80 with initial conditions as follows. This is for the K10, this is for K20, K40, and the K80. As you can see, all the bus can go to the desired path, and if you can see more, it is intuitive that by increasing the K, the control became more aggressive. You can see it took longer for system in the K10 to follow the path or to be stable than the K of rather than K80. And also it can be classified for of the objective function that is shown in table here. As we increasing the value of K, the value of the objective function somehow becomes smaller, which is the system performance is increasing. So this is the first part simulation with variation of the initial condition. We have for initial conditions, I mean, to conduct this simulation, this is the first, second, and third, and fourth initial condition. You can see here, and this is the result. And you can see from the four initial condition of the system, the bus still can reach the point of equilibrium. I mean, they can follow the desired path, or they can be stabilized perfectly. So it can be proved, it can be said that it is proven that the system is asymptotically stable. And then this is first part real-time implementation. The left side is real-time implementation result with variation of K, and the right side is real-time implementation result with variation of system initial condition. We use K like before, K10, 20, 40, and 80 for the real-time implementation. So it can be observed.
Sorry, Nadana, your time is more 5 minutes more.
Okay. Thank you. So it can be seen that the controller can make the bus follow the path perfectly, and it also can be seen here. The objective function that as we increase the K, the objective function also be smaller, so the system is increasing. It also, you can see also in here the real-time implementation that in any initial condition, the system can go to the desired path perfectly. And this is the second part, simulation and implementation. The left side is the simulation, and the right side is the real-time implementation. For the simulation, we use variation of K are 60, 70, 80, and 90. Meanwhile, in the real-time implementation, we only use K 80 and 60, as this K can bring the system to the path faster. So you can see this, that our result by simulation or real-time implementation, the proposed algorithm of the path following controller can bring the bus into the desired path perfectly. Okay, so we can conclude from all the implementation and simulation result that the proposed path following control can bring the autonomous bus system to follow the desired path. And by using the formulated steering control function, the bus system will always go to the desired path wherever it started with any possible initial condition, because the origin of the error is assured to be asymptotically stable. And also the objective function also plays a major role to determine the base K value for the controller that will affect the aggressiveness of the controller. Okay, these are references that we use in this research. Okay, thank you. That's all for my presentation. Then time and place, I give back to Dr. Ali. Thank you.
Oh, thank you, Nadana. Any question for Ms. Nadana? Very interesting, because Indonesia is still developing bus transportation.
Sorry, Dr. Ali, I have one question if you allow me.
Okay, please, Muhammad Abu.
Yes, interesting topic. The question is about the experimental implementation.
Yeah.
Like your optimization depends on optimizing the error and the desired path and actual path. So how did you measure the error? What sensor did you use?
Okay, basically thank you. I'm sorry. Thank you for your questions. I will try my best to answer your question. So I think it is interesting that I see that this is we doesn't use any error indicator to see if it's great or not, as the objective of our research is to follow the path perfectly. So I think it is one missing in our. I have to say that this one is this is something missing from our research, that we does not use any error indicator like RMSE or IAE like that to present the error of the system. That's all that I can explain to you.
Okay, is it answer the question?
Yeah, Mr. Mohammed, is it? I'm sorry if I can satisfy your question.
Thank you. Thank you.
Okay.
Okay. Now, thank you for Miss Nadana, and then we know continue with the fifth. Yeah.
Okay.
The fifth presentation. The title is Development of a Robotic Arm and N Effector for COVID-19 Testing by Mr. Muhammad Abu Al-Maluk from Hashemit University, Jordan. Okay, Mr. Muhammad, the time is yours.
Thank you. Just let me put the mic on.
First, let me share the screen. Okay. Thank you so much, and hi everybody. The subject I'm presenting today, it's about development of a robotic arm and end effector for COVID-19 swab testing. This work was done by Hazem, Fadi, Zaid, Michelle, and myself from the Mechatronics department in the Hashemite University in Jordan. I'd like to start the talk with this figure taken from the World Health Organization. This was taken on November 12, 2021. It shows that more than 250 million confirmed cases and more than 5 million confirmed death cases were reported by that date. And this is because of the coronavirus or the COVID-19 virus. So everybody knows that this virus hit us all hard in almost all aspects of our life. And the way we are conducting this conference is just an example of that. It's having it to be virtual because of this virus. So I think everybody knows that COVID-19 is diagnosed using what is called the PCR test. This test is usually conducted manually by healthcare workers. The problem is that this manual methods bring the health workers in close contact with the
either infected or suspicious to be infected persons. Sorry. So, we know that the healthcare and co-op workers play the most important role in fighting the COVID-19. So we need to protect them as much as possible. And we know all that there are protocols, equipment, and protecting tools available to do so. And we, as an engineer, we need to do our part. So one of the way to try to protect the health workers is to investigate implementing robots in fighting COVID-19. Now, this figure here has been taken from the IEEE Robotics and Automation magazine recently in March 2021. It shows some of the main areas where robots can be implemented. First, we can implement them in prevention, like UV disinfection, in screening, like in vital sign monitoring, diagnosis, like in swabbing. This robot here is taking a swab from this person here, or in treatment, where sometimes if the patient gets very sick, we need to put a tube to make him or her breathe better. So some people investigate using robots in intubation systems. The topic of this paper belongs to this category, the diagnosis, and more specifically, the swabbing type. I just want to go quickly through a couple of slides to review some literature, other researchers who did similar work. In this recent published work in 2021, soft pneumatically actuated robot consists of a conical shaped end oropharyngeal swabbing. So oropharyngeal means swab through the mouth or from the throat. So this is an example of some of the recent work on this topic. Another example is this 9 degree of freedom redundant rigid flexible coupling robot. Again, this robot conducts the swabbing through the mouth. And the last one I want to show you, it's again a recent work in January 2020, which means naso means it's through the nasal cavity through the nose. Now, quickly, I need to talk about the two types of swabbing methods that are adopted globally. So there are two types. A, shown in the figure on the left, it's the throat oropharyngeal, it's through the mouth. And B, it's the nasal or nasopharyngeal swabbing, it's through the nose. Now, which one is better? At least in our work, we decide to go with the second type, the nasopharyngeal swabbing, which is through the nose, for two main reasons. First, literature shows that this method provide higher viral load, which means it will most likely gives better or accurate results. The second reason, in Jordan Ministry of Health, this is the adopted swabbing method. So this is why we choose to implement the swabbing the way it is. Now, I just want to talk briefly about the COVID-19 specimen collection that is adopted by Center of Disease Control, CDC. They have a long report that, but I just want to highlight 2 points. First, they recommend that the patient head should be tilted back 70 degrees when collecting the nasopharyngeal specimen. So the patient head should be at 70 degrees angle. And this is to enable the doctor to insert to be parallel to this, what is called the plantain bone, this bone. Doing so is important because the nasal cavity has tissues that are very delicate, and we don't want to damage or hurt the tissue in this area. They are very sensitive. So what happened is that when the coworker insert the swab and to have it parallel to the plateau bone. It goes inside until it reaches this area called nasopharynx. This is a very sensitive area. The doctor should be very careful not to hit this area hard because it's very sensitive and it's very close to the brain. So then what happens is the doctor rotates the swab and retract it. So this is how it's done manually. Now, let's start with our proposed robotic system. So based on the CDC report I just mentioned before, we decide to build a head holder. The figure on the left, or figure here, the figure shown on this side, this shows the solid model of the head holder we designed. And we decide to go with designing a manipulator with a 3 degree of freedom articulated robot, and also to design a custom 2 degree of freedom end effector. So both models were built as we shown this figure on solid model, and we use the 3D printing technology to convert the design to the real robot you see on the right side. So this is the 3 degrees of freedom. This is joint 1, 2, 3, and this is where we have the end effector, the 2 degree of freedom end effector, which basically consists of prismatic and revolute joint. And this is the head holder, and this is HASM, one of the group. This figure here, I can talk, it shows the end effector in much more detail. This is the end effector here, and it consists of this is the prismatic joint, and we have a screw motor that allow this part to slide on this blue rail. And this is the revolute joint, which rotates the swab clockwise or counterclockwise. Now, it is very important to control the contact force between the swab tip and the human nasal tissue, because as I said, this tissue at the end of the nasal cavity is very sensitive, and you don't want to hit it hard. So we decide to put a fence, as shown in the figure. It's just 1 degree of freedom strain gauge. So this force sensor or strain gauge, it's only measures the force along this direction, the normal direction. The proposed robotic system is basically an active sensing and control of the contact force. And this is very essential. Let me go back a couple of slides here. Yes. If we need to, like, let's put it this way, humans have different distance for the nasal cavity. Like, we don't share the same distance here. It's different from one person to another. So we can't use a position control, because any slight difference or error in positioning will hit this area and may damage it. So we need to have a force control while the swab inside the nasal cavity. So that's why we decide to have the active sensing and control force control. Based on literature, they reported that a range of force between 0.35 Newton and 0.68 Newton were suitable, and it will not cause congestion or injury to that sensitive area. So we conducted some preliminary experimental tests. What you see here on your left side is a real size head phantom model. We have it in the medical school in the university. It's a medical model that the nasal cavity in this model is similar to the real cavity in a human. So we conducted some tests on this phantom model. And what we see here on the right side, this is the normal contact force response during the swab sampling test. So first thing to note is that the whole test took like less than a minute, about 50 seconds to conduct the whole test. And the test is divided to 3 stages. Let's start at time 0 here. Time 0, the manipulator moves the swab, and this is done manually by an operator who is far away from the patient and control the robot remotely. So first, the operator move the swab and bring it close to the opening of the nose with the angle, as I mentioned, the 70 degrees angle, which this head holder help us to get. And then it comes the end effector rule, where it starts inserting the swab. And here we see that the force increases until it has this peak, which is about 0.6 Newton, which represents that the swab reach the final destination. It can't go further. And with the active controller, we managed to control the impact force or the contact force not to exceed the 0.6 Newton, which is safe according to the literature. Then during this region here, we have the collecting the viral, like the swab is rotating clockwise and counterclockwise. And the last stage where we have the swab retracting, that we remove the swab out of the nasal cavity. So we conclude that the normal contact force was successfully controlled and maintained below 0.68 Newton, which were reported in literature to be a safe and comfortable amount of force to conduct this test. Finally, conclusions and future work. A robotic system for COVID-19 nasopharyngeal swab sampling was designed and built. This robotic system consists of a 3-degree of freedom arm, 2-degree of freedom effector with force sensor. The robot is controlled remotely and from a safe distance. The preliminary results we conducted on the real-size head phantom model show that we were able to maintain and control the contact force below 0.68 Newton, which is essential in protecting the interior tissue of the nasal cavity from any injury. Now, future work, we know that we still have long road to go through. We're thinking of conducting further quantitative studies, probably on human volunteers. Also, we need to improve the position and force control, accuracy, comfortability, and also we need to see, like this robot, what is the success rate of PCR test, like put it on a real test and see how good is the sample we obtain. Well, that's all I have. Thank you, and I'll try to answer your questions.
Okay, thank you, Mr. Muhammad Abdul Al-Maluk. Okay, any question from participants?
Hello, Mr. Ali. I have one question.
Okay, please, Mr. Justin.
Hello. Okay, thank you. Hello, Mr. Muhammad. I just curious about what is the reason why do you not use camera in your NF vector? Because similar research mostly using camera for positioning their NF vector. Why do you not use camera? Thank you.
Okay. The camera would be like if the person is far away, you're right. If I think if the person operating the robot will be far away and can't see exactly where this swab is going, yes, we need a camera. Definitely we need a camera. Like, but currently we are just in the first stages. Like we didn't test the system on COVID-19 patients, so we still can see where the swab is going. But you are right. Once we have the vision, you can't see where the swab is going. Yes, we need a camera. Exactly.
Okay, thank you, Mr. Muhammad.
Okay. Okay, thank you. And any else from participants? Okay. The time is okay. Now, thank you for Mr. Muhammad Abu Melu. Thank you for your presentation. And now we continue with the last presenter, Mr. The title is Kinematic Design of Integrated Rotational Axis Mechanism for IGUS Delta Robot from by Mr. Leonard Brusley. Okay, Mr. Leonard Brusley, time is yours.
Thank you. Thank you all for the opportunity for me to present this at this conference. And I would like to share a little bit from our projects on kinematic design for Delta Robot. Okay, I'm sorry. Okay, is the full screen showing?
Yes.
Okay, great. I think I would like to. Okay. So let me introduce the project before we start. The project was a cooperation between IGUS, Beckhoff, and Swiss German University. This is the first stage of the project at IGUS booth in the manufacturing trade show in 2019. It's a 3-axis Delta robot. They sell bushings for machines, and because there is a need for the controls, they only sell the mechanical frame and the mechanism for the Delta robot. There is a need for the electrical actuator and also the control software. That's why we form a cooperation between SGU, Beckhoff, and IGUS. The actuators is supplied by Beckhoff, and the control software is supplied by SGU. Now, after the development of this Delta robot that is complete and able to be commercialized, there is a need for the additional rotational axis. And this is where we develop the project for a further development. The Delta robot, as you know, has 3 degrees of freedom that is incapable of rotational axis during the pick and place. And its superior speed makes them a choice for, whenever you need speed, people use Delta robot for pick and place. Unfortunately, you can only move from A to B and not be able to rotate the parts. Now, for some applications, that is a limitation. And so the project here is to add a rotational axis to the 3 translation axis of the Delta robot. So we are able to rotate the object during the pick and place motion. This shows the working envelope of the IGUS Delta robot that we developed before in the phase 1 of the project. And we want to maintain this working envelope, and whatever rotational axis that we add to this Delta robot should also be able to reach to the ends of the working envelope. Now, I mentioned before that the end effector of a Delta robot is very light compared to a arm robot. For example, here you see that the arm robot has actuators at each joint of the arm robot and making them very heavy in terms of its inertia. The Delta robot is not. The end effector of a Delta robot is very light. It's only at the end here, and the arms tends to be very light. So again, whatever we add to it, not the end effector. For example, this to do is just add a stepper motor or a servo at the end effector. That will be the natural solution. But however, adding a motor at the end effector will defeat the advantages of a Delta robot. So we will add a kinematic linkage such that The servo for the rotational axis can be maintained away from the end effector, but also connected to the end effector via some kinematic linkage. So that is really the goal of the project. We came up with some design concepts, mounting the motor here and having a telescoping axis here, but the telescoping axis will add too much inaccuracy by having multiple pin in a slot joint. We also consider mounting the servo way up top and then having 2 pin in a slot joint, having a sliding joint on the middle frame here, and having 2 universal joint. However, this also have too many degrees of freedom that will create some indeterminate positions. Therefore, what we came up with finally is a telescoping double universal joints. A single joint of universal joint is like this, but it does have a fluctuation in terms of the angular velocity. The double U joint will provide a constant velocity as long as we maintain the input and the output shaft on the same virtual plane. However, to maintain the working envelope, we also need a telescopic motion. So in summary, we came up with a double U joint with a telescoping member in the middle. So something like this. However, we will accomplish this using a slightly different geometry. So the one U joint on the top here near the motor, another universal joint near the gripper, and a sliding middle member as a telescoping member. Like I mentioned, the universal joint will have a speed change at the bend angle of like 45 degree. The fluctuation is very, very significant, which makes it subject to vibration and all kind of problems. And so by having a double U joint, this will remove the speed fluctuation. As for the motor selection, well, we made some assumptions in order to size the motor. We assume we will need a cycle time of 0.2 seconds for one rotation, rotating the end effector, an acceleration and deceleration of 35 milliseconds. So there is a ramp up and there is a ramp down. This just further improve the reliability and also longevity of the joints. So we do want acceleration and deceleration rather than an abrupt start and stop. This will come out to be 380 RPM at the maximum or constant velocity. Taking into account the moving mass moment of inertia, using our solid modeling software, we can calculate the mass moment of inertia. It comes down to 2 times 10 to the minus 3 kilogram meter square. This acceleration, which is 196.4 radians per second square. Therefore, the torque for the acceleration and deceleration needed, assuming no friction, because they are insignificant compared to the acceleration and deceleration, the required torque for the servo will be 0.4 Newton meters. The motor selected then is the Beckhoff AM8111, which delivers a 0.16 Newton meters of torque, which is plenty adequate for our needs. Here are some of the motor mounting and coupler. We use all EGUS bushing because obviously we're doing this for EGUS product. Therefore, any spare parts preferably will be an EGUS product. They are plastic bushings that are self-lubricating, maintenance-free bushings. And so serves our product very well. Here is an example of the pin in the slot sliding joint for the telescoping member. Here's the top motor mount and the bottom motor mount. We make this to clamp to the existing structure, so we do not make like drill any holes or make any permanent modification to the existing frames for now. In order to save space, we have to make the T joint, the T member of the universal joint in such a way so it saves us space. A design of the solenoid gripper is also made such that it is very compact, and we are able to just use a very simple solenoid with a very short stroke. The mechanism shown here that we designed allows us to have an additional, we redirect the gripping force from the linear stroke vertical into the horizontal motion, and therefore creating a gripping action. It is located at the end effector here. So after the implementation and fabrication, we have done a reach capability test. The first one is on the extreme top of the working envelope. The second one is at the extreme low point of the working envelope. And so you see that the pin in the slot the telescoping member will extend to its maximum length. Here it is at a minimum length. And also we need to test the maximum side boundaries of the working envelope. And here the telescoping member is also almost at the maximum, but not as far as the one reaching to the bottom of the working envelope. And so here are some sample pictures of the actual implementation. Here is at the top, here is at the bottom, and here is at the extreme edge of the working envelope. Again, this is using existing back-off servo motors. And this one is a preliminary model using a stepper motor, but in the actual implementation, we use back-off AM8111. We did also some tests for the positioning error. Here is an example of a step input. Notice that the time is pretty short. So this ramp up is not that slow, really. I mean, we're talking about 1/10 of a second here. And there is an overshoot, a slight overshoot of the controls because it is not yet tuned. The closed loop parameters are not yet optimized at the time of writing of this paper. So we see there is some overshoot and then it settles down into the target set point. There is some inaccuracy due to the pin in the slot joint, the telescopic member. They are about 0.2 degrees, I believe. And hold on, let me look it up again, just to make sure I got this right. It is 0.1 millimeter dimensional tolerance on the 3D printer. And therefore, this translates to about half a degree in the rotational axis. Now, we do have 3 points where this can introduce an inaccurate position and introduce a backlash to the kinematic linkage. One at the top U-joint, one at the telescoping member, and another one at the bottom universal joint. The backlash being measured by the servo here is about negative 0.5 degrees to about 0.6 degrees on the forward motion. And then going from 90 degree to 0 degree, we see also a hysteresis or a backlash going on here. Now this will be further, obviously much better once we get to an aluminum pieces and metal CNC machine members of the linkages rather than a 3D printer. So we believe a combination of the PID tuning of the servo as well as some better machine kinematic linkage will reduce this error very significantly. Let me play the video demo of the implementation of this rotational axis. So it is called fourth axis, basically it's the rotational axis. So we programmed the demonstration to test the outermost position, rotate, and also do a test run on the back-off PLC controllers. So picking and place at different points here. And also we will have another test with the gripper rotating. So this is a package for a demonstration in the manufacturing trade show that we usually have every December or every November. And they're actually commercializing this as we go. Hopefully, it will enhance the features being offered by the Delta robot. That is all from me. Thank you for your time, and I hope we share some useful information.
Okay, thank you, Mr. Leonard. Any question from audience? Okay, there's no question anymore. Thank you, Mr. Leonard, for your interesting presentation. And now, as our last, Mr. Muhammad Abul, please.
Thank you. Very, very interesting topic. Just want to make sure I understand. You added that telescope joint, which is a passive joint.
Yes.
Okay. It's so there is no fluid. It's not a hydraulic. It's not pneumatic. It's just
It adjusts as the 3 axis of the Delta robot moves. It will stretch it, and it will basically follow through with any motion from the original 3 axis.
And it didn't affect the workspace at all. Like the workspace stays the same as original.
Yes, that was the challenge. We have to come up with a geometry that will accommodate the same workspace.
I just want to, like, why didn't you think of using a spherical joint? Like, what's the problem with spherical joints instead of the universal joint?
We can also do spherical joints. It's not as simple to implement, but yes, that is definitely possible.
Because if it's a passive joint, well, you don't need to control it. It's gonna give you more degree of freedom. So
right.
But it might not be strong enough as
we can do a constant velocity joint, but there is a torque being transferred from the servo controlling the rotation. So there is no translational. The translation it's passive, but rotationally it's active.
Yeah. Sorry. Yeah, you're right. Okay, thank you.
But constant velocity joint is also an alternative, but it's just a bit more complex in its geometry.
Thanks.
Yeah, thank you.
So, okay. Thank you, Mr. Muhammad Abu Maluk. Also, thank you for Mr. Leonard Priestley. And now, our audience, as our last presenter has concluded this presentation, I would like to give appreciation for all presenters and all attendees here. Thank you for the insightful presentation and discussion. I also apologize if there is mistake in name pronunciation. Also, we will send presentation certificate to by email for its presenter. And see you next time in the next morse conference next year. Thank you, and we close this session. Thank you.
Thank you so much, Mr. Ali.
Thank you. Waalaikumsalam.